Lesson 2 on the topic of algebra focuses on consecutive integers between a set. Now, let me break down what this sentence means. If we look at the word consecutive, it means quantities that follow each other. Then the phrase consecutive integers would mean that we have integers that follow each other in an ascending order, meaning from smallest to the largest. So for example, if I have two numbers 1 and 2, these numbers are consecutive. They are integers, of course, because in lesson 1 we spoke about what integers are. But they're not just integers, they're integers that follow each other. The 2 comes after the 1. If I give you, say, two numbers, or let me say in this case 3 numbers, 21, 22, and 23. All these 3 numbers are consecutive integers because each of these numbers is an integer and they follow each other. 22 follows 21 and 23 follows 22. And we say they're in an ascending order, meaning they move from smallest to the biggest. 21 is small to 23. 21 is small to 22, and 22 is small to 23. In other words, 23 is bigger than 22, and so is 22 bigger than 21. Then the other focus will be us understanding the word set. The word set means the nth root of a whole number. That gives us an irrational number. So when we say an nth root, we're speaking about something that looks like this. The nth root here is an n. And n here would be any number that is a natural number. In other words, n can be 1, 2, 3, and so on. In fact, our n normally would start at 2. We don't necessarily have a root of 1. So our n here would start at 2, 3, 4, going like that. So when we say nth here, we mean any of these numbers can be replaced by the n there. And b would be a whole number, because in this case we're saying, when we're looking at a set, is the nth root of a whole number. That will give us an irrational number. In other words, this number that we're going to get, the whole number that we're going to get here, when we take the nth root of a whole number, we're going to get an irrational number. So these numbers, we spoke about them again in lesson 1. We could have something like the square root of 2. Remember that here we have an invisible 2. We don't usually write that invisible 2. We can also have the square root of 10. Now, both these two numbers are irrational numbers when we take the nth root, in this case the square root of those numbers. We can replace the n here by a 3. We can change it to a 3. Maybe we can have a number like the cubic root of a 15, or we can have the cubic root of 5. Both these two numbers are irrational numbers, and the numbers inside the cubic root are whole numbers, and we're taking the nth. In this case, our n, the nth root, in this case our n is a 3. You can do this with the 4th root, you can do this with the 5th root, the 6th root, right? As long as the number that we get here would be an irrational number, and we have here a whole number inside that nth root, then that number will be classified as a set. Now let's go back to the whole sentence to then try to make sense out of it based on all this information that we talked about. If we say that we are looking at consecutive integers between a set, we actually saying that, let's say we have our set. I'll just take the simplest one, like a root of 2 is a set, right? As we defined a set, it's an irrational number, which we say it's a set, right? Now, we're saying here we're going to look at two consecutive numbers, meaning two numbers that will put this number in between. Obviously, if they put this number in between, it means the other one will be this side and the other one will be this side. Such that those numbers, you'll find that, let's say one of them can be a number 1, such that this number, so 1 is less than the root 2, and the root 2 would be less than a 2. Therefore, root 2 is an irrational number or a set that lies between 1 and a 2, right? It's in between those two numbers. Now, one may ask to say, why do we bother to find two consecutive integers, right, that put a set in between, or that put a rational number in between them? How does that help us? Why do we go through so much trouble trying to find these numbers, right? The answer to that would be, if you look at sets or irrational numbers, oftentimes we don't have a feel of what type of numbers they are, right? Is this number a big number or a small number, right? Is it in the order of magnitudes that are your 0 point something, or is it there at the top like your 10 point something or 100 point something? It's oftentimes difficult to tell compared to the rational numbers, right? So this is to say that if we were to draw perhaps a number line, right, we know that we're going to have a 0 here, we're going to have a 1, we're going to have a 2. Remember that our number line will extend those numbers until infinity, and this side we're going to have a number 1, this side we're going to have a -1, a -2, and it will extend like that until negative infinity. Now, what I'm saying is that we don't know where the root 2 would be. But if we then do this method where we find these consecutive numbers, because remember, these numbers, they follow each other, they're next to each other from small to big, as we explained what consecutive mean. So it means now we have an idea to say this number lies between 1 and a 2. It's a number between that range or that graduated scale. In fact, if you were to remember in lesson 1, when we were discussing irrational numbers, we spoke about this specific number, root 2, and said that it is an irrational number because in decimal form it is equals to 1.141213, and it goes on like that without ending. It is a non-terminating number. That's why it's an irrational number. And the other property of this number is that after the decimal point, we don't see a recurring pattern here. We don't see numbers that repeat themselves, and that's how we defined irrational number, right? But you can see from this decimal form of this number that it is actually 1.41. It's a number that is between 1 and 2. In fact, if I were to draw it on the number line, it's a number that is somewhere here, right? It's a number that is somewhere there. Then this is very helpful for us because we now have a feeling to say how big or how small is this number, right? So basically what we're doing here is that we are estimating the sets. We're doing an estimation of sets to say what is the estimate of that number, right? What type of number is it, right? To do these estimates, we are going to use a theorem that says that if you have A, B, and C, right, being positive whole numbers, and A being less than B, B being less than C, then the nth root of A is less than the nth root of B, and the nth root of B is less than the nth root of n. So what does this theorem mean? This theorem means that if you take any numbers that are arranged in such a way that the first one is less than the second one and the second one is less than the third one, right? And all those numbers, those three numbers that you take, are positive whole numbers. Then if you take the nth root of those numbers, it will also have a pattern such that the nth root of the first number is less than the nth root of the second number, and the nth root of the second number will be less than the nth root of the third number. Now let's say now I take random numbers. Let's say I choose to take the number 4, and I also take the number 5, right? And I also take the number 9. Clearly you can see that a 4, a 5, and a 9 are positive whole numbers, right? If you need to revise what whole numbers are, please go to lesson 1, where we discuss these different number systems, right? Now, these numbers are not just positive whole numbers, but 4 is less than a 5, and a 5 is small to a 9, right? It's less than a 9, right? Now this theorem, so this is the first condition, is that they are whole numbers, and this one is the condition that they are in a way that 4 is less than a 5 and a 5 is less than a 9. The conclusion of this theorem says that if this is the case, if you have a numbers that are of this form, right, then these numbers must behave in such a way that if I take the nth root, remember nth root will start from 2, 3, 4 going upwards. I'm going to use a simple one like a 2. So I'm going to take a square root of a 4 here, right? This square root should be less than the square root of a 5, and the square root of a 5 should be less than a square root of a 9. So just to fix this quickly, we prefer normally not to write the 2 there, because a square root already has an invisible 2 there, right? Now, if we simplify this further, you'll know that the 4 inside the square root here can be rewritten as a 2 to the power 2, right? So that now I change this square root. Remember in grade 9 we said that the square root is the same as 1 over 2, right? So this will be less than a 5, and then here we're going to have a 3 to the power 2 is the same as a 9, and I'm also going to change the square root to 1 over 2. Now the 2 and a 2 would cancel, and the 2 and a 2 will cancel also here, so that now I'm going to be left with a 2 is less than root 5, then is less than a 3, right? So this is what the theorem says, right? And you can see that this is true, because if you look at this, the 2 is less than the root 5, and the root 5 is small to a 3, right? And we are able to do this without a calculator, right? We are able to do this with, we then have an estimate. It means on our number line, if I come between the numbers 2 and a 3 somewhere here, right, that's where you'll get a root 5. And in fact, we can check the root 5 using a calculator to see what is the square root of 5. And actually it comes out to be 2.23607 and so forth, right? And you can see that that number is less than a 3 and is bigger than a 2, right? So this is a theorem that we are going to use when we try to find two consecutive integers that put a set in between. Now I'll jump to example 1 to apply this theorem and find those numbers, right? The example 1 reads as follows. So let me firstly start off by putting that. It says now here, determine two consecutive integers between a 10. So if we have a 10, right, as our irrational number, as our set, right, which two numbers, right, will put this number in between? They will be here on this number in between, right? The first step here when we solve this problem would be that we look for what we call perfect squares. So I'm going to put a less than and a less than because I know that those numbers, the other one will be small, the other one will be big. That already I know. But these numbers here, I'll put what we call perfect squares. Now the question would be, what is a perfect square? So this is what the first step says, is that you need to put the set in between two perfect squares. But what is a perfect square? A perfect square is a number whose square root is a whole number. And here they've given me examples of perfect squares. So let's say, for instance, I take the square root of 1, right? So the square root of 1 should give me a whole number. We know that 1 can be written as 1 to the power 2, and here we can write that so that this and this cancel each other, and now I'm left with a 1. Do you see that when I take a square root of 1, I get a 1. So the 1 that I've get as an answer, I've found as an answer, is actually a whole number. So I took a square root of 1 and I got a whole number. It means 1 must be a perfect square, right? It's a perfect square. It's a number that when I square, right, it gives me a whole number. It's a perfect square. The same is true to say if I take the root of 4, right? Remember that 4 can be rewritten as 2 to the power 2, so that I have 1 over 2. And these 2 and 2 will cancel. My final answer would be a 2. Do you see that this 2 is a whole number? This 2 is a whole number. It's a number that's sitting there, right? It's a whole number. So it means 4 is a perfect square. It's a number that when I take the square root, I get a whole number. It's a perfect square. You can continue doing this, maybe even for a 9. If I take this 9, I take the square root of 9, right? We know that 9 can be rewritten as 3 to the power 2, so that now here I have 1 over 2, and this would cancel each other, and I'm going to be left with a 3 there, right? But a 3 is a whole number. A 3 is a whole number. So I took the square root of 9 and I got a whole number of 3 is a number here, right? So that means the 9 must be a perfect square. And you can continue doing this for all the whole numbers, right? 1, 2, 3, 4, 5, 6, 7, 8. So basically, if you square any number, even if, let's say, for instance, you square a 9, we know that it's going to give us 81. So that means if we take the square root of 81, right, it's going to be a square here. It's going to be 1 over 2. And it will cancel the 2 and the 2, so that I'm left with a 9. With a 9, yes. So that means the 9 is a whole number, right? And we got this 9 by taking the square root of 81. So that means the 81 must be a perfect square. It's a number that when you take a square root, it gives you a whole number, right? So there are many numbers that would increase here, giving us perfect squares as we increase our whole numbers as well, squaring all of them, right? So now here we have to find two perfect squares, one that is this side and one that is that side. And obviously from our theorem, when you look at our theorem, the perfect square that should sit this side should be smaller than the number that we are given. In other words, the perfect square that sits here should be smaller than a 10, should be small to a 10. So which perfect square is smaller than 10, right? We know that that perfect square is going to be a 9. I mean, you can look at it from these numbers here. You can see that a 9 is less than a 10, right? And definitely a perfect square that will be greater than a 10, a perfect square that will be greater than a 10 would be a 16 here. We can clearly see that here as well, right? So 10 is between here 9 and 16, right? Between those two perfect squares, right? That's the first step, you determining two perfect squares, one that will sit on the left, which is going to be less than the number inside the square root, and the other one that will sit on the right, which is going to be greater than the number in the square root. Now, because we are dealing with a square root here, right, the second step would be for us to then put square roots on both sides. We're going to put the square root on a 9, and we keep the square root of 10 the way it is, and we put the square root on a 16, right? And at this stage, we know that 9 can be written as 3 to the power 2, and we can convert the square root to 1 over 2. So this would be less than 10, the root of 10, and 16 can be written as 4 to the power 2, and here we're going to have 1 over 2. Now, this and this would cancel, that and that would cancel. At the end of the day, I'm left with only a 3 being less than the root of 10, and the root of 10 being less than a 4. So at our answer, this is our final answer, where we're saying the root of 10 is a number that is between a 3 and a 4. Right, is a number that is between a 3 and a 4. So this means on a number line, this means if I were to draw a number line, just to have an understanding, if this is 0, right, somewhere here I'll have a 3 and I'll have a 4, right? The root 10 is a number somewhere here. The root 10 is a number in between here. The root 10 would be a number somewhere here. Let me write properly here. This pen is failing me. So the root 10 would be a number somewhere here. It's a number between a 3 and a 4. Then we have an estimate of how this number looks like, right? So I have a study guide here that explains all these step-by-step processes that I'm doing here. And to get access to this study guide, please follow the link in the description of this video, right? So it will explain everything. So this should be your final answer here. Let's try example 2, where we're working with a cubic root, right? Example 2 says to us that, so this is example 2. It says to us, between which two consecutive integers does the cubic root of 15 lie, right? So if we have a cubic root of 15, which two numbers, right, do we have on either side of this cubic root of 15, right? Which two numbers squeeze this cubic root of 15? Now, to do this one, because we have a cubic root here, we're going to find two numbers here that we call cubic number, a perfect cube. We're going to find two numbers that we call a perfect cube, right? Because it's not a square anymore. We can't find perfect squares, right? But the question would then be, what is a perfect cube, right? A perfect cube is a number whose cubic root is a whole number, right? So what does that mean? So they've given us examples again here. So this means that if I take a cubic root of 1, right, it's going to be 1 to the power 3, which is just that, but here I'm going to have 1 over 3. And this would mean now that I'm going to be left with a 1. Now notice that when I take a cubic root of 1, I get a whole number, right? I get the whole number, right? Because 1 is a whole number, it's part of the whole numbers. Then this means that 1 is a perfect cube, right? We can apply the same technique on an 8. If we take the cubic root of 8, this number here, right? We take the cubic root of 8. We then are going to have a 2 to the power 3, and I can rewrite this as 1 over 3. Right, so that this and this cancels, and then I'm only left with a 2. Now if you check a 2, it is a whole number, right? So 2 here is a whole number. That means the number that we took and put it under a cubic root must be a perfect square, right? So 8 is a perfect square. You can continue the pattern with 27. Take the cubic root of 27. This would be a 3 to the power 3. We're having 1 over 3 here, and we're going to be left with 3 because this would cancel, right? Now the 3 is a whole number. Do you see that? 3 is part of the whole numbers. And here is our 3 here, right? So that means that 27 must be a perfect cube. And this continues like that even when you take other whole numbers like 4, 5, 6, 7, 8, and you cube them. When you cube these numbers, right, they'll give you a number here, right? That's such that when you take now the cubic root of that number, it then gives you that whole number that you started with, right? So for instance, I can say 10 to the power 3, right? 10 to the power 3 should give me 1,000, right? So this should give me 1,000, right? But if I take the cubic root of 1,000, right, I'm actually going to be left with a 10 because the 3 and the 3 there would cancel. Then it means 1,000 somewhere here as we continue until we get to 1,000. 1,000 must be a perfect square because when I take the cubic root of 1,000, it then gives me a whole number somewhere here of a 10, right? A whole number of a 10 somewhere here, right? Now, using our theorem, right, we're going to look for a number that is less than the 15, right? We're going to look for a number that is less than a 15 on this side. A number that is less than a 15, right? But this number has to be a perfect cube. This number has to be a perfect cube. So if you look at 15, a number that is going to be less than a perfect cube that is going to be less than a 15, right, would be an 8, right? It would be an 8 here. You can see that number here is going to be an 8. But the number that is going to be a perfect cube that is going to be bigger than 15, this side here, right, is going to be a 27. That's what our theorem said, right? Remember, I'm choosing these numbers because already I know that even in the square roots, they are still less than, right? That's why my second step on this would be, well, not on the square root, but on the nth root. That's why my second step would be now putting the cube root, right, on both sides as well. Why? Because we are dealing with a cube root here, right? So I'm going to then put a cubic root here and a cubic root here, right? And this would mean that now I'm going to have 2 to the power 3, and this I can change to brackets like that, and here I'm going to have 15, then here I'm going to have a 3 to the power 3, which would give me 1 over 3. Now the 3 and the 3 will cancel, the 3 and the 3 would cancel, so that my final answer should be 2 is less than the cubic root of 15 is less than a 3. So this means that the cubic root of 15 lies between 2 and a 3, right? So if you were to draw this on a number line, our 2 would be here, right? So this number is somewhere in between these two numbers. Now we have an estimate. We know where it is, right? And we know that it's a small number because it's somewhere here, right? It's not far that side, or it's not even negative, right? Again, the example will explain the same things in detail